All right, let's jump right in. Have you ever looked at a massive nuclear power plant and wondered how abstract, mind-bending physics equations literally turn into the physical realities that power our cities? Well, in today's Explainer, we're demystifying that exact process. We're going to take a step-by-step journey, starting from the microscopic life of a single neutron, all the way up to the macroscopic physical design of a whole reactor core.
Okay, let's dive into this roadmap. We're starting with sustaining the chain reaction, then moving into the thermal utilization factor. After that, we'll look at math for infinite reactors, followed by the six-factor reality, and we'll wrap it all up with designing the perfect core.
So, part 1, sustaining the chain reaction. To really wrap your head around a nuclear reactor, you kind of have to start thinking about neutrons like living organisms in a microscopic family tree. It's literally a story of generational survival. The health of the next generation relies entirely on the environment we build for it. And that brings us to the ultimate engineering problem. How on earth do you keep a nuclear reaction going without it just dying out? You've got this massive population of neutrons, and if that population drops to zero, your reactor shuts down. It's a constant, incredibly delicate balancing act.
Let's look at how this survival actually works step by step. In step 1, a single original neutron is absorbed in fissile fuel. Step 2, that specific absorption event creates a second generation of neutrons. And then in step 3, the absorption of those second-generation neutrons gives rise to the third generation, and so on. According to our source material, from one generation to the next, the neutron population in the reactor multiplies by a very specific factor. Well, provided none of those neutrons physically leak away from the core, of course.
Moving right along to part 2, the thermal utilization factor.
Now, here's a critical truth about our neutron family tree. Not all neutron absorption is actually helpful to us. We really need a way to mathematically separate the good absorption from the bad, and this is exactly where the letter F comes in. The thermal utilization factor, or F, is simply a ratio. It's the number of neutrons absorbed specifically in the fissile fuel divided by the total number of neutrons absorbed in the entire reactor. That includes all the neutrons swallowed up by the moderator, the structural materials, the control rods, the whole shebang. So why does this ratio matter so much? Because only the thermal neutrons that are absorbed in the fissile fuel can actually cause the thermal fissions we need to generate power. And this brilliantly illustrates the exact battle happening inside the reactor core at all times. We've got our primary goal, that slice representing neutrons safely absorbed in the fissile fuel. But, they're constantly competing with those other slices, neutrons captured in the moderator or hopelessly lost to the structural and control materials. Reactor engineers are constantly fighting to maximize that first, absolutely vital slice of the pie. All right, part 3, math for infinite reactors. Let's zoom out a bit and look at the actual mathematical formulas from our source text that govern these perfect ideal settings. Equation 3.14 defines the multiplication factor for an infinite reactor. See that little infinity symbol right next to the K? That means we're imagining a reactor so massively huge that we can just completely ignore any neutrons leaking out the sides. So let's break down what this actually means. The neutron population multiplies by a combination of 4 distinct variables: eta, epsilon, p, and f. So K infinity equals eta times epsilon times p times f. In physics, this is famously known as the 4-factor formula. Now, the text notes something pretty fascinating. If the reactor were made only of pure uranium-235, the variables p and epsilon would be exactly 1, or unity. But pure U-235 just isn't practical. So instead, engineers treat this formula like a desperately important checklist. They're striving to keep the values of p and f as close to 1 as physically feasible to keep the whole reaction perfectly balanced. Which brings us to part 4, the 6-factor reality. Okay, it's time to pivot away from the theoretical chalkboard and look at messy physical engineering. Here's the stark contrast we actually have to deal with. Our infinite reactor is hypothetically large enough that neutron leakage is completely ignored. It's a perfectly closed system. But a finite reactor, the real-world system we literally have to build with concrete and steel, has physical edges. And because it has boundaries, the leakage of fast and thermal neutrons out into the environment is completely inevitable. We're going to lose some of our population. Let's see how reality upgrades our previous math. Here we have equation 3.15, straight from the source material, which introduces the effective neutron multiplication factor, commonly known as KF.
Because we have to account for reality, our original four-factor formula gets a very necessary upgrade. Now Kf equals our original eta, epsilon, p, and f, but we multiply all of that by two brand new variables, PNLF and PNLT. So what are those? They're our final mathematical hurdles. PNLF is the non-leakage probability of fast neutrons, and PNLT is the non-leakage probability of thermal neutrons. Simply put, these represent the statistical odds that our neutrons do not escape the physical bounds of our finite core. If engineers can balance all 6 of these factors, the chain reaction survives in a finite space.
And finally, part 5, designing the perfect core.
Now, what's really interesting about this slide is, well, this is the climax of our explainer. How do engineers actually take these abstract probabilities, factors, and ratios and use them as a blueprint to literally build a physical reactor core? Take a close look at this diagram. It's a physical manifestation of all our equations arranged into a neat, orderly lattice. This specific layout is what's called a heterogeneous thermal reactor core. You might be wondering, why design it this way instead of just pouring everything into a giant vat? Well, early on, in theory, one might have considered a homogeneous mixture, just mixing the fuel, moderator, and structural materials uniformly together. But as our source quickly points out, that is highly inefficient for those crucial math formulas we just looked at. Instead, engineers use a heterogeneous lattice. They place distinct bundles of fuel rods at discrete, carefully calculated locations within a surrounding pool of the moderator. So the crucial point is that reactors aren't just big vats of mixed-up material. Their geometric layout physically forces the math to work in our favor. By placing the fuel in this discrete lattice arrangement, it actually enhances the depth traversed by the neutrons within the moderator. This achieves better thermalization, greater resonance escape, and ultimately increases that vital P times F product we saw in the formulas earlier. The math literally dictates the physical reality. Which leaves us with this final, remarkable thought to ponder. If complex mathematical equations literally dictate the exact physical shape and layout of a massive nuclear core, what other invisible mathematical blueprints are secretly structuring the world around us? Keep that in mind the next time you look at the engineered world. Thank you so much for joining me for this explainer. Keep seeking out the structures behind the surface, and I'll catch you in the next one.